All right, so let's wrap up the lecture part today. Maybe within the first hour, there'll be two activities that we would like you to do that would span until next Monday. All right. Um, so how's everyone on the class activity so far? Not too bad, right? Huh? How do you what? Input what? Sorry.
Do you have any guides?
Oh, yeah, that's a great question. At some point we will gradually do that. So it will basically will be building up for your lab. So today we'll first learn about the OS structure. Then we talk about process management and the signal. All right. How many people have heard about signal? How many people run infinite code when you do syscale and then you're like, what do you do to stop that? Control C. What does Control C actually do? It sends the interrupt. So basically, that's a way for who to signal to whom.
For me to signal to kernel.
For the user, for you as the user to signal to the kernel, so like, hey, do something about this. Is it the kernel or is it the program that you want to kill? Think about it, it's the program, right? So there are multiple things involved. So think about it right now. There are multiple things involved. The user, which can be random, I mean, human or random. I can just have my cat literally walking through my keyboard, typing different keystroke, right? And somehow my computer has to respond to my cats. I have the S in that because that happened before. Two cats walking on a keyboard at the same time. Not fun. All right, but let's first talk about the structure of the OS. All right. So the first type is what we call monolithic kernel. And then we have this thing called microkernel. So we'll go through some of these on a high level detail. All right. So here is what you might have envisioned your OS is going to look like, right? Something that you start with, you have the hardware abstraction layer. These basically allow you to abstract the hardware, which is an awesome thing, right? And then most of the components, as you can see here, will live inside the kernel. What do you mean by that? So, pointer, right? From your system skill, you learn about virtual memory, right? And you learn that there's this thing called page table, right? Have you ever wondered who populates the page table? Like when I start the machine for the first time, right? That table has to have something. Then when someone called malloc, and then when I use the address, it should be a legit physical address. So who did that job? Yeah. Right? So basically, in the system skill, you might recall that the OS and the hardware work together because the hardware gives you a specification that say, hey, do this, do this, do this, followed by this. Then the OS like, I'm gonna do this, followed by this, followed by this, followed by this. When you write the OS, basically most of the job will be like, okay, what does the hardware want? I'll do exactly that and make sure my user don't kill me by saying this is too hard to use. I'll abstract basically what the hardware can do for the user. All right. File system. Anyone know what does file system actually do? What are some of the main things that they do for you? All right, raise your hand if you use file on your computer. You should raise your hand. If you're not raising your hand, you're sleeping. Everyone needs to use a file, right? Who manage that? The file system. There can be multiple ways you can build a file system, right? Imagine, for example, let's say you have your normal Windows, like I have my normal Windows machine right here, right? I can build a file system that works really well for a desktop because I can assume that I will be the only user at any given time because that's my laptop. I'll basically be the one using it, right? And I can optimize our system for that. I can also think about the data center, right? Where many files are now shared across server. Now imagine, what do you do? Anyone use network drive before? How about Google Drive? Yeah, imagine who take care of those things. What if, right? Situation, what if I have a share folder, I upload a file, your friend also upload the same file with the same exact name, what will happen? Actually, I don't know what happened in that case. Anyone tried that before? Like you update the same file on Google Drive at the same time by two users. Yeah, maybe try it out because that also involves like who get to actually save the file, right? What if two people try to save at the same time? You see both of you see the older version. You update it, right? I feel like I might not be correct, but I feel like the default would be if I see someone update, I'll update that. If I see someone else updating the file, I'll update it too. I just write over it, and then you lose something, right? You the first guy who gets overwritten over will lose the update, right? So that's the choice. That's the design choice. Then you have things like Windows Manager, networking. You install. Anyone realize your motherboard comes with the Ethernet board, like Ethernet like connection, right? That's kind of by default, and there's a lot of magical thing going on, which you learn a lot more in module number 2. But there's also networking elements, right? And then there's a device driver that drives every single hardware. Then there's this thing like buffer allocation. For example, let me give you this one example, right? Let's say I have this hardware right here that takes in data, and I have my program that want to pumping in data, but let's say my hardware can take let's say I can take 64 bytes at a time, but my data is 2 terabytes long. What would happen? Well, it'll blow up, right? I'll just have to send 64 bytes at a time. Now that's one program. Let's say I have, oops, sorry. Let's say I have a second program coming in, want to use the same hardware, right? Now the bono gets complicated. Who gets to use the hardware at that point? Then one solution is to maybe have this buffering. Why is that useful? So that, for example, maybe the first program can just pump in the data it wants to send and then move on. It will move. It basically will say, hey, I put everything in the buffer. The hardware will keep taking those things and process it for me. I can then move on to the next thing, right? So that's the buffer allocation, buffer manager, basically try to manage this spare space that I will allocate for my connection between the software and the hardware. And then that's this system call, exception, and interrupt, which we learned quite a bit last week. And in the system, well, in most of your programming classes so far, you handle exception before, right? Divide by 0. Or, for example, let's say, what's the HTTP 404? 404. Yeah, I type in some not correct address, right? You cannot find the website, right? Who handle that? Should Chrome just go out and never tell you anything? Or should it report the error number and say, hey, the website not found, right? Who handle that? Then we talk about signal and interrupt. This is the trade-off. This is the trade-off. As I said, once you're on the system design, a lot of things are making the right trade-off for your user and for your hardware. So here, the portability, let's say I switch new hardware, right? I will have to make sure this hardware abstraction layer works with a new hardware, because how many people upgrade your computer before in your life? We all did it, right? At some point. I mean, by the time, let's say you guys are like 19, 20 years old. Now I feel old. But at some point in time, let's say your family would have to upgrade your computer, right? Buy a new desktop, buy a new laptop. Well, somehow the same OS will have to manage the new hardware. So I need to make sure the abstraction level works with the new hardware as well, right? Then how many of you also born in a day where you have to install drivers? What are these drivers you have to install? What are the common ones that if you don't do it, your game do not work? Graphic driver, right? What are the most often updated driver actually? Huh? Sound card that also works as well. But you also might have realized that, for example, you plug in a new mouse, you have to update the driver. Really, right? It kind of works from the get-go. You plug in a printer, it will make sure you put in the right brand for some OS. For the newer OS, it detects everything, right? Magic. But the hardware abstraction layer also have to deal with that, making sure the driver is updated. So here's some trade-off. Simple. This is simple between like the interface between components are simple. Everything is centralized inside this monolithic kernel, right? Low overhead in terms of managing everything. I am the center of everything. I know how to manage everything, right? Disadvantages. Protection against error. For example, let's say one component is going off and there's like error happening to the OS. For example, some of the blue screen that you might have seen might have been from bugs in the virtual memories of system. And the OS like, hey, that looks odd. Let me crash everything, right? Dependency nightmare. How many of you guys run into that already? Louder, so to share. Yeah, right. How about you?
I have no idea.
Oh.
Oh wait, are you talking about like kernel stuff or like just dependency error?
Yeah, dependency error.
Oh yeah, poetry.
Huh?
Poetry.
Poetry. All right. How many of you here took fun part already? How fun was that when we're trying to figure out what version of Rust and Scala that you have to use for each assignment? Yeah. When you install each version, somehow it worked with the kernel, right? It worked well. And then someone changed the API, say, hey, this API then requires another library, right? I have one sample of that, right? I was basically when I was doing research, I worked with a software that can simulate a GPU. Basically, it's a software I've written that would fake out here is the GPU, right? And then it worked with GCC 4.4, which is a really old version of GCC. Also worked with G++ 4.4, which also means that back in the day, if I want to test anything, any software on that, why are you wearing mask like that? It's like really odd. Can you actually properly wear it? Yeah. Right. Yeah, by the way, that type of mask doesn't really like protect anyone else. Cool, thank you. So also means that I use for that particular simulator, I need to use CUDA 4. At the time of my experiment, the newest version of CUDA is CUDA 7. All right, CUDA 7. Also means that the application wants GCC 5.4. This is what my simulator wants. This is my application that I need to run. What does it mean? Nightmare. I have to compile the application with the version more than 5.4. Then I compile my simulator with 4.4. And then I need to make sure that the compile application works with CUDA 4 to get everything to run. Right? So you might have seen this a lot when you are now in the industry, because sometimes people don't update their code that often, just not enough team to do everything. Right? There's also, for example, you download a piece of software, say, hey, you need to install this library for this version. One of the most common things that you would run into that would fail your installation is pick the wrong version. If you use monolithic kernel, everything has to work kind of perfectly. You need to make sure for whatever program you run, it works for that particular version of things, right? So dependency nightmare can become an issue. Now here's microkernel. Microkernel is a little bit different. There's a privilege mode inside the microkernel, and then you see that the hardware abstraction layer is now separate thing, right? And then my idea is to keep the minimal operation in the kernel. I do the least I can do inside the kernel. Oops, sorry. And then for the rest, I'll just trust that I'll set everything up correctly afterward. If I want to install new component, I don't have to modify a lot of the kernel. I just need to add this support. I'll handle the rest either through the application, to the device driver, to the memory. Like see how file system is not a part of the kernel. How device driver is not a part of the kernel. Memory manager also not a part of the kernel. You can design the kernel this way. What's the key thing that would look so different from monolithic kernel? See who get the privilege. Just the kernel, right? So you think about it this way. If you require privileged access to the hardware, put that code as a part of the microkernel, the rest outside. So that's kind of like usually the design concept. When yes. Huh? The last sentence. Basically, the observation here, right? The privilege mode is just within the microkernel, but then things like device driver is not privileged anymore. You see that? The memory manager is not privileged anymore. The file system is also not privileged, right? You can design the file system that way. It actually, there are also different file systems that when you do it this way, it actually can get faster as well, right? Here is the key. If you require privileged access for anything you do here, what do you have to do? Put that code in a microkernel. Make sure there's some APIs you can call from your application, and you call it. Basically, if you require privileged access for any action, put that in the microkernel, but just that's it. The rest outside of the kernel, right? So here's a trade-off. First of all, it's modular. If my file system breaks down, I then just fix the file system. I don't have to fix everything in the kernel. Isolation also is great. If something is performed poorly, like let's say my memory manager performs so poorly with whatever I set up right now, I switch it out, replace it with a new memory manager. That's it, right? Disadvantages, now you have to talk across all the components because, let me go, do you mind if I go back one slide here? They're not a part of the kernel, right? So if I have to talk between these two components, I have to find a way for them to talk, right? I have to find a way for these two components to talk. So this is the communication over here. So the performance might not be as good in certain aspects. Most of the time, one thing I tell you that there are ways to improve the disadvantages. So this is actually a pretty popular design nowadays in a large scale data center. To think about, okay, how do you minimize the job of the kernel, and then I can build whatever services I want to build on the user level. Yes.
Yeah, like a hybrid thing.
Great question. Some experimental, but by experimental, I mean, yes, hybrid. Let me. Now, any question about EOS abstraction before we move on to processes and process management? All right. So here's the process abstraction. When you have a process, think of it as an instance of the program, right? It defines things like protection boundary. You, by this point, should love the segfault as your friend that protects the memory from illegal access, basically. And one process cannot disrupt another process. And this is managed by the OS, which is a great thing. imagine if you have to do this on your program, right? When you write a multi-threaded program for the first time, you have to do some, it's not a process management, but it's thread management, which is really annoying to get it right the first time, really annoying to get it right the second time, really annoying to get it right even now for me. Sometimes I have like shared data and I forgot to lock them. That can happen. Process managed by yours. When I said manage, when I have to create a process, when I have to queue the process, or when the process gets to run. All right. And on the right side here, you see the physical memory. Whenever you see the physical memory, think of DRAM, because that's what it is. The physical location of things. This is your code. This is kind of like your raw data associated with the program, right? And in Cisco, I kind of just like deploy at least some sense of like what happened when you run a program. Basically, when you run a program, these things have to be in your memory. Then it has to initialize the heap and the stack, right? Because you would need that for function call for the stack, for memory allocation for the heap, right? So these things are gonna grow over time, right? Then your instruction and your data get copied over to here and here. Then what? Run the first line in main function, right? What do you mean by that? The program counter would point to the first line on your machine instruction, and then you keep going down. It's as simple as that. Now, that's your process. OS kernel also have their own thing, right? Just to keep in mind, OS kernel also have their own thing. Because kernel, again, is a piece of software that's used to manage everything else in your computer, so they also have that, all right? Now, single thread process works this way. Again, stack discipline, right? I have a range of addresses, heap grows up, stack grows down. The stack holds local variable that you use. For example, when you call a function, you have something like this, like function int add, right? Int A, int B, right? Int C equals A plus B, and then return C, right? The local variable C, I mean, to be honest, A, B, and C are all local variables that these things are managed by the stack. It has to make the state for A, B, and C so that they can be run. Then malloc. How many of you sick of malloc already? Good. You'll do more. Well, actually, I think I should say the word good because malloc is really annoying to manage, right? So it would be great if you can come up with a memory management scheme that doesn't have to deal with malloc. I mean, imagine how many languages doesn't require malloc. A lot, right? So why can't we do that? Anyway, dynamically allocated data are in the heap, so it grows in a different direction. The data section store any global or static variable because you know it's going to be there. There's no point in growing on the stack because everyone see that from the get-go. The code as some text. Sometimes we call this text. That's your program. Your program, again, your program is a part of the data that you run, right? The program counter basically holds the location of the next instruction. And the way you manage the state of a process is this. All right, when you have a program and when you run the program, you first admit the process, right? You admit into the system. Then the process generally have two states, run or not running. It can be running or it can be not running. Ready means that I can run. Ready means I can run. Dispatch, not dispatch. So I can dispatch the process and run them. Now, when I am running the process, right, I can finish the program and it exits. I terminate the process. I can be running the program and scanf. What does scanf do? Take your input. What if you throw the computer and never put in the input? What happens? Just keep waiting, right? So you can have things like interrupt and the IO wait. That, for example, I can do scanf, waiting for my input, right? Here, and once it's complete, it becomes ready again. I can issue an interrupt, and then it becomes ready. For example, I can I can tell the process go to sleep. Go to sleep means stop. Don't terminate. Pause the execution. Let someone else use the CPU. All right. So that's the state of the process. But the key idea is the transition between running and not running. And when I'm not running, am I ready or am I waiting for some IO? If I am waiting for some IO, I cannot run. I have to wait until the IO finish. Quick note of that, there are things like asynchronous IO we're not going to talk with right now. Let's assume things are synchronous and I need to finish my IO before I continue running, right? Now, here is some more detail, right? Some more detail on managing the process. So inside, there's this thing called a process control block, all right, that manage the process. All right, so the process control block is there to manage everything that goes on about the execution, the running of the process, right? Why? So let's say I have a program that calls another process. I have to build the relationship, right? For example, I have Steam open. The Steam then run a game. I should be able to tell that the game that I'm running is also kind of being launched by Steam, right? So that's a parent and child relationship. Who spawns what? All right. Then I need to be able to identify the process by, well, what's the easiest way I can identify something? Huh? Yeah, just give them a number, right? I can have a number from 0 to whatever number I want, right? So that's a process identification number. Now, priority is one interesting thing. How much do you care about a print job to a printer? Is it okay if I delay that by like 5 seconds? Yeah, I don't care, right? How about your game? Should I delay, like, when you click something, should I delay that thing by 5 seconds? No, right? You die in the game. So, process also has priority. One good example is gaming, right? Your game typically will have high priority. Why is that? Those are interactive applications. You're basically playing them. The user play them right now. So that better have highest priority, right? Things like Spotify may be medium priority compared to games because, I mean, it doesn't really use a lot of resources. I can buffer your music for like 3 songs and hopefully within the next like 10 minutes, I get to download the next 3 songs. Program counter and register, these are obvious. You need that to run. Pointer to process memory, also obvious. You want to make sure you know where is my process in the memory. And here, the limit, right? How much memory can I allocate? List of open file. Why is that important? How many of you forgot to do fclose on C assignment? Yeah, we do that a lot, right? So let's say the program exits normally and I have the list of open file. What can I assume? I better close them all, right? So that's another thing about like fclose, right? You should do it regardless in case the process gets killed by some, like it gets murdered by someone, like another user kill the process. Then you better be able to close the file. Basically, the PCB structure is a giant, not giant, actually, these are pretty small in terms of kilobytes, but it keeps track of the process, right? And now when you have to start a new process, what do we need? First of all, I need a functional PCB state. Right? I need to know who is the child, who is the parent, where's the program counter, how do I run them, right? I need to make sure the actual code is in the memory. That's another important stuff, right? I run a program, I need to make sure that binary from a file get copied over to the memory and make sure the program counter say, hey, that's the first one, right? And I need to allocate the space for the program's data, right? I need to also have to prepare the user kernel space, right? I need to make sure that the memory is well managed. Now, oops. Is that the same thing? Okay, so this is actually things to do. First of all, I will first allocate and initialize the PCB. Right, these are the action. And then I have to allocate the memory for the process. If I have malloc, that I know for sure. If I have the global variable, I need to allocate that. I need to copy the program from the disk. Yes.
Does the different processes have like different?
Yes. Each process. Do you mean process or processor? Process. Yes. Each process has their own PCB. Because otherwise, if they are shared, yes, nightmare. Why? The kernel has to check the PCB for the state, which means that if I want to modify the state at their share, right, it's gonna be really odd when, let's say I have 4 CPU running 4 processes, I have to update those things in parallel. The easiest thing, each process gets one. All right. Also, much easier to not share. Yes.
They're all
Huh?
yes, put in the RAM.
Yes. Think of the RAM as like that's the only place you can store something that is bigger and doesn't have to register for that. Yeah. Because even though you have the notion that cache exists, cache are not programmable. As a programmer, I can say, hey, I want to use that part of the cache. Those are all hardware managed. So the only location is the RAM, which actually simplifies the software development, right? Because when I want to get anything that required memory, all in the RAM. Should I bring it up? So here's the expansion of your question. Definitely not going to go through your exam. This model might change in the future because now you have new technology that can have like terabytes of RAM, but it's a different, totally different RAM. How many people heard about this Intel Optane technology? Look it up. Basically now it supports a totally different RAM. It's different type of RAM that is way bigger. But the downside is they're slower. The way they handle write looks more like an SSD, where anyone know that you guys know, right? That when I have a lot of writes to SSD, it dies. That type of RAM behaves the same way. Because the way you program that type of RAM, you put electrical shock to that cell. Now people are still, including Intel and many other companies, are trying to figure out, okay, how do we use this thing? Because it gives you a lot of capacity. But then, do I use that to store my file? Do I use that to store my parts of the memory? Do I use them for both, right? Because I can now use it. Can I treat file as a part of your memory? So that this thing that now pops up that would change the abstraction going to maybe 5 to 10 years. I would say 5 to 10 years kind of window, to be honest. That's why that question that can we assume everything is in the RAM? Yes. Will that change? Maybe not. But you might have more capability coming from your RAM. So for each user level stack space, basically from the user land, if I need the stack, I allocate them. Basically, if I need anything in the RAM, make sure you allocate that from the kernel. Manage it for the user. Then allocate the kernel level stack to handle any system call and interrupts. We'll go into this soon after the break. Basically, oh, sorry about the diagram. Then right before the program starts, you copy everything from the arguments into the user memory. For example, you have like you run a program and there's some input arguments. Make sure they pass through the user memory so it knows what's the argument that's coming in, right? Then you transfer the control to a stub that have the function that just called the main function. This hopefully will answer your question. When you write the main function, who called that? The stub called the main function with all the argument as your input. See how it's called the main function with argument 1, 2, and 3. Then when the main function finish, the stub exit with the return. See how main take a return code, right? Many of times you do like it main and you return 0, but you can return other number. That means that the stub will now see that number. That's how you can communicate across processes, basically. So to create a process, we can use Unix fork. The fork is a system call which will create a child process to the process that's called a fork. And both child and the parent will run concurrently. When I said run concurrently, it means that they run at the same time. Why is that possible? Your CPU now have multiple cores, right? So why can't I launch the parent and the child at the same time using all the cores? That's possible. Child process will inherit these from the parent at the time of the fork. Note that it's at the time of the fork, not after. So I'll get my program counter. What does it mean? So let's say I have a parent, right, that run a program for a while, right? This is my program, and this is where I fork. And this is my program, right? When I fork is like I copy the entire program over and the child run it, right? Here's the thing. It starts running from this point, not this point. It starts from at the point of the fork, not before that. Why? I copy the program counter over. Again, repeat of what I just said. When I fork, I make sure that the child starts from here and keep running. Everything else that the parent did, well, I copy them in the CPU register or the open file and the stack and the heap. Basically, everything gets copied over. Now, the child has a copy of the stack, the heap, the file that are open, and the register. Everything will look the same, right? But after you fork, that's when you can have the parent do one thing, the child do something else. For example, let's say I have a Steam, right? I then run a game. It means that Steam will do whatever it has to do afterward. Maintain the Steam client, then my game basically get run, right? Return value of the fork, this is a little bit something that you have to kind of either memorize or know that they exist. When I finish, the return value of that, when I call the fork function, less than 0 means that I cannot create a child. 0 means that it returned to this newly created child process. More than 0 means that it returns to the parent or the caller. Now you might be confused, like, what the hell? All right, what the hell? So let's say you might erase my code, like what I draw here. Okay. Now, let's say this is my program, right? And I do something, and then I fork. And here's code after the fork. Why do I need either zero return value or non-zero. For the code after the fork, how can I know is that a child or is that a parent? Because it's the same code, right? It's the thing about it, that's the exact same program. But then I have to make sure that I have a way that say, hey, now I am running the parent or I am running the child, which means that a typical trick. Now I'll zoom in. Let me zoom into this. I'll say int id equal fork. I call fork with some integer that takes in the return value. If id equals 0, what can you assume about the inside the bracket? Is that the child or is that the parent's code? Who will be running that? Basically, when I fork, I just don't randomly call fork without getting the return number. I have that number stored in my variable. And then I have if id equals 0 means that that bracket will be run by the child, right? Because if I'm a child, the return will be 0. It's just for me to identify, hey, I'm a child, so let me run that. Else, if id greater than 0, this bracket will be run by the parent. That allows me to basically fork a process and have them run two different codes inside the same program. Inside the same program. Again, this is one single program, right? But the if side will be run by whom? Who has the return 0? Child or parent? The child will run the if part. The parent will run the else part. All right. So that's how you can now fork the process by writing one single program. Got it? Okay. You try this in the lab. So just be aware why you need the return value. That's so that you can now manage both the child and the parent. So now the process also has yes.
So the child process depends on the parent. Like if we kill the parent process, child also.
Great question. To be honest, the default is like if I kill the parent, the child dies. There are some OS that would assume that's not the case. So yeah, I know it's really like that sentence sounds so wrong on so many levels, but yes, in a computer, if you kill the parent, the child dies with the parent. How many times I say that still sounds so wrong? But that's also you can write the OS in a way that it doesn't happen. But then you have to figure out how are you going to manage all the child because that will become the zombie problem. It becomes there's no parent. So how can you identify this process with no parent? Because this abstraction is easy to manage. I can have a process tree where the system D with the process ID number 1. That's like when I boot up, that's the first process. Yes. That's great solution. So a lot of OS, if I want to maintain the child, they get promoted to everything becomes the child of system D, right? Because now I have another parent, so I become the orphan. I'll just let system D handle my process. That's one possibility. Yes.
So, okay, so for example, if right, if batch is here, then we will be a child of system.
For Vim.
Like in that.
For here, right? Yes, you can make that design. It's a design thing. Yeah. So you can have Vim as the child of system D when bash gets killed. In your Linux, that's not the case. If bash gets killed, Vim die. Yes. Can you have multiple parents? I don't think it's possible with the abstraction we have right now. I don't think it's possible actually in any shape or form. Because if I fork, like, I cannot think of the scenario where I have two processes and they call fork and they spawn one child. There might be a way to make the child inherit something from the second process, but they're not going to be forked by the second process. It'll be someone to fork that. Uh-huh.
That's possible.
Wait, what?
But it's still forking.
So I fork from where? Sorry, I cannot hear you. Uh-huh. Yes, I fork Vim from bash. Well, because it's also like kind of like a grandchild of system D, right? That would inherit whatever system D has. Because the assumption is if I'm a child of someone, I inherit something from the parent. Now I'm a child of the login D, it's a child of system D, and afterward bash is a child of login D, which means I inherit from my grandparent. Now Vim will be inheriting from the great grandparent as well with this model. Then if the two want to communicate, right? Let's say I want to make sure there's a communication here. Communication. I use a different way for the two processes to communicate. I don't make them interrupt. I just let them talk. Right? So in Unix, the command execute exec, right? Exec will load. It will load a program into the code section to execute it, right? Now think kernel. Think kernel. Your step is not just running the main function. You have to load the code as well, right? So let's say I fork with the PID, right? If it's less than 0, you see a fork fail. If PID of 0, is that a parent or is that a child? Child. The child should get 0. The parent should get the ID of the child. Why is that model working? How many child can I have? I can fork as many, right? So I just need some non-zero number to identify each child. But the child to identify itself, I just need one number. So I use 0 to represent that. So in the child process, I can say, hey, I'm a child process, so I execute /hello, right? Else, this is the parent. I mean, you can write whatever code in there, but let's say right now just parent resuming, that's it. Right? The new process retains the process ID, environment variable, and the file descriptor. The CPU statistics and virtual memory is a new one because it's a totally new process. They have their own address space. All right. So there's multiple variants of the exec function that depends on the input of my exec. It can take, for example, a path, the location of the executable you want to run. That would allow you to be able to go to that file, put that file into the memory as a program and run it with the arguments, right? You can put in the path, you can put in the file with the arguments. You can also have the path, the argument, and the environment in the environment variable here, right? So there are many. It's like you can also put argument as an here. See, it's an array, a pointer. So each of these versions gives you the ability to basically pass in different types of arguments. Or the other thing is like handle a path or file. Yes. Yes, exactly. Yes, it will be called when the kernel say, I want to schedule the process. So the code will be there. And then when I schedule the process, it will start to run this program. Then you have to wait, right? So you fork, you have the parent, you have the child run a code. For example, your Steam game, that would be like a legit. I execute my Steam game so I can run, like the child basically run a game. Parent is the Steam client, which would basically keep maintaining the status. Then when I exit, right, over here, notice how parent basically will be waiting. And when the child exits, I resume. So when I call the wait function, I can make this possible. If I don't wait, both of them run concurrently. Now, if I want to have this execution model where I run a child until they're finished, then I resume, I can call the wait. Will block the parent. Basically, this allows me to block the progress of the parent until one of my children exits. Yes. Why do you need to fork? Imagine if you are running Steam client and you want to run a game without forking. Basically, this fork allows you to execute a program. Basically, this forking is done so I can run a totally separate program in the child process.
So why do we wait?
Why do we wait here? That depends on what the parent has to do. In some cases you have to wait until the child finish. Let's say I have a synchronous scenario where I am running a main program, and the main program has to spawn a service that say I want to access the database until I got the database query back to me. I don't have the data afterward, right? I can then fork a child, process that, gather the data afterward, and resume. So in that case, you can use the wait command. And with this, after the child terminates, the parent resumes the execution. And if only one child terminates, the wait will return the process ID of that child. If more than one terminate, you pick arbitrary child number and return that PID. All right, just to make note of that. Let's say two of them finish at the same time, you get a random PID. And when wait return, that also defines the exit status using a pointer. That will define any possible error. So if any process has no child process, wait, will it wait? I have no child process, so it will not wait and return -1. Like, what the hell? And then to determine, I said exit status is done using a pointer, right? It's through WIF macro. So I can call WIF exited inside here with the status from the child to specify I exit normally. WIF signal with the status means the child exit because some signal are not caught. Then you can call, well, you can then call a macro WExit status, return the code, the status code when the child exits. This will give you the signal number that kill the child, that terminate, the terminating signal. If stop, as the name suggests, when the child is stopped, it gives the number of the stop signal, so I can handle that if I want to. Like, for example, I hit Control C. The parent can handle, if the child get killed by Control C, and they can handle, hey, some signal kill my child. Here's what I do, right? The process will execute the last statement as the OS delete the process. Because, I mean, when I'm done, EOS come in and clean everything up, right? And then I do the exit system call, which return the exit ID. The wait command will allow me to return the status data. The resource that I allocate so far for my process get deallocated by DOS. So if you allocate something, don't forget to free. Again, kernel code usually is written in C. So yeah, you have malloc and free to make sure that everything works correctly. The parent may terminate the execution of the children using abort syscall. Let's say the parent detects something, like detect some signal, say, hey, kill that process. I can call abort. To rest a syscall, some of these can be like Bashal use a lot of allocated resources. That makes some bugs in the program, right? So it's better abort. If I spawn a child and say, hey, I don't need that anymore, abort. I don't need that process anymore. I'm done. I'm exiting. Someone kill me, so I better abort the child, right? If the assumption is the OS doesn't allow the child to continue, then the parent should call abort on all the child. Some OS will also eliminate all the children if the parent is terminated. We call this type of OS cascading termination. This whole thing is called cascading termination. Why is that possible? The OS has a PCB, right? The structure that maintains the status of the process. So I know the parent, I know the child. So if I'm killing this process, I then know all the child process ID, which then I can send kill, which kill the child process. The parent process may wait for termination of child process using the wait syscall by doing this. Wait pointer to the status code. So when you have this, right, then you can do the W exit. You remember the macro W exit something with status as an input? So let me go back a few slides. Here, you see how I use the status as an input. And at this point, what the, right? These are macro, which I can use this guy as an input to check if that process was stopped, was killed by some signal, or exit normally. So I use that macro. I pass in the status here. That's a pointer that I call as a part of the wait command to check the status of the child when the wait finish. If no parent is waiting, process becomes a zombie. Yes. Yes. Yeah. Basically, when I have the wait function call, I can pass in a pointer called status. Basically, I can pass in a pointer, whatever I want to call. I can call it S, A, B, C, D. It's a pointer. It's the after. Basically, this becomes a pointer, right? And then with that, I can use these macro to check. If I do W if exit and put in the status and then becomes true, it means that hey, it exits normally. Yeah.
Also, we use WF exit
in conjunction with the status after the wait. All right. If parent terminated without invoking the wait, that process becomes often because parents are not waiting for a child. Parent die. The process is adopted by the init process. System D. Now, let's do a quick break. Now I'll let you vote. Basically, we have one more topic. This used to be a separate lecture. We can do it now. We can do the activity now and do the signal activity afterward. Your choice. So should we do a maybe 10 minutes break? Resume the activity with process management only, not the signal. So activity 3. Then next week we come back, we talk about signals. We will then cover activity 4. Is that okay? But I thought that we finishing earlier, but we have a lot of breakers. Yes. we don't have class this Thursday, so we come back Tuesday. So activity 3 is still next Monday. Yes.
Is it a separate lecture?
Oh no. So if let's say the plan is to stop here, do activity 3, it means that you have to go to your first, next lecture, and activity 4 will start next lecture. Yeah. So how about we do that? It's a little bit later than I expected, so let me do this. We stop here, we then start activity 3. Hopefully many of you will finish activity 3 in class, so you have to worry about that afterward. Then we come back on Tuesday, we talk about signal, and then we resume from there. All right. Okay, so let's do a 10 minutes break. And I'll be back here answering any questions about the process management.